So welcome. Welcome to the Planetary Fluid Dynamics Seminar Series. I'll just send a little, I'll put a little information in the chat here. So if you'd like to be getting email reminders, you could just send me your email address in the chat and I'll send it out on the weeks that we have talks happening. Next time in 2 weeks, on the 12th of May, we have Aymeric Spiga from Laboratoire de Meteorologie Dynamique, and he's going to talk about studying the atmospheric dynamics of giant planets with global climate models. Today, we have Luna Hiron. She got her PhD from the University of Miami in 2021, and she is now at a postdoc at Florida State University. She's talking to us today about the long-term coherence of frontal eddies around the Gulf of Mexico's loop current. So why don't you take it away, Luna?
Thank you, Jonathan, for the introduction, and thanks for inviting me. So I'm doing my postdoc here at COAPS, but I'm going to be presenting the last chapter of my PhD. So I got a PhD in meteorology and physical oceanography from Rasmus, University of Miami. And I'm going to be talking about long-term coherence of frontal eddies around the Gulf of Mexico's loop current. And I would like to acknowledge my co-authors, Philippe Miron, who is also here at Florida State, Professor Nick Shea and Bill Johns from Rasmus, University of Miami, and Professor Eric Chassinier and Dr. Alexandra Bozak from Florida State. So before we enter in the Gulf of Mexico and the loop current, I like to give a little bit of a zoom out and look at what's the role of the loop current in the whole ocean current system. So this is a schematic view of all the surface currents in the world. And so the red arrows show warm currents that propagate and flow from the equator to the poles. So these currents are responsible for distributing the heat on the Earth and bringing very warm waters from the equator to the higher latitudes. And the blue arrows are cold currents that in turn, they bring cold waters from the poles to back to the equator. And this flow creates this gyre. So we have, each basin has its own gyre. We have North Atlantic gyre, South Atlantic gyre here. And each gyre has its own western boundary current that it's composed of this arm or this part of the gyre that brings warm water up to higher latitudes. So if we zoom here in the North Atlantic gyre, actually we have the Caribbean current, we have the loop current, the Florida current, and then which becomes then the Gulf Stream. And so this is an image from satellites. So is velocity derived from altimetry. And we call this velocity geostrophic velocity, but you can see this velocity of the water that goes from 0 to 1 meter per second. And here you can see very well the western boundary current for the Northern Atlantic gyre. So composed of here the loop current, you have the Florida Strait and the Florida current and the Gulf Stream. So for this talk, I'm going to be focusing in the Gulf of Mexico, and in particular in the loop current system. So the loop current is the only current in the Gulf of Mexico, and it's the most energetic feature. So it flows from the Caribbean and brings very warm and salty waters into the Gulf of Mexico. And this current turns anticyclonically, so clockwise, and exits the Gulf of Mexico through the Florida Strait, and then become eventually the Florida current. So every 6 to 17 months, the loop current sheds an eddy. So the loop current eddy forms and then detaches from the main current and bring warm and salty waters to Mexico westward. And so we have a third element that's composed the loop current system, and this is the loop current frontal eddies. So these frontal eddies are actually cyclonic eddies, so they rotate counterclockwise. They have a cold core eddy, and they're called frontal eddies because, of course, they propagate in the vicinity and the outside of the loop current front. They have diameters that can reach values of up to 120 kilometers, And they are generated through instability of the loop current. So when the loop current becomes stronger, deeper, it sheds some instability, and there's transfer of energy from the loop current to the ambient water, the Gulf waters. And then you have the formation of the cyclonic eddies around here. And so this eddy can stensify and then grow on the neck of the loop current and squeeze this neck to lead to the detachment of this eddy. We're going to be focusing in this little cyclonic eddies, the frontal eddies. And so we have these three features that I'm going to be talking along my talk: the loop current, the frontal eddies, and then the loop current eddies. And why do we care about the frontal eddies? So the first reason is because they play a very important role in the shedding of the loop current eddy. And this is a mechanism, this is a process that we've been, as oceanographers, we've been trying to understand for the longest time. So we know some mechanisms that lead to the shedding of the loop current eddies, but we cannot predict with accuracy with a month in advance when a shedding will occur. And currently, there are many proposals that are being funded to study this. And so better understand when this frontal eddies intensify and the reason why they intensify, maybe they can help us predict better when a loop current eddy detachment will occur. Then you might ask yourself why there's so much money involved in that. Well, there's many reasons why people are interested, or oceanographers are interested in understanding when a shedding occurs. One of them is because this eddy carries water that flow very fast around the eddy with velocity that can reach up to 2 meters per second. And so when this loop current eddy propagates westward towards Mexico, it reaches very deep waters where oil platforms are located. And these oil platforms have to shut down completely or partially to avoid damage to the structure and risk to the workers. This is one reason. Another reason is because these eddies that I said, they're formed from very warm and salty waters. They have a lot of heat in their interior, and that can work as fuel for hurricane intensification. And so this is a map of ocean heat content of the Gulf of Mexico. You have red color, so very warm, and so structures with a lot of heat, which is corresponding here to a loop current eddy. And we have overposed to that the track of Hurricane Ida. So Ida crossed the Gulf of Mexico, and when it entered the Gulf of Mexico, actually was in a category 1, and rapidly, when it crossed very warm waters, it moved very fast to a Cat 2, 3, and then 4 before hitting Louisiana. And so understanding well in advance, 1 week or 2 weeks in advance, where the structures are going to be is very important. And on the other hand, the loop current frontal eddies that are smaller features, as you can see here, there's a blue blob, right? They actually apport and they bring a lot of cold water to the surface. And so they can have an opposite effect to the hurricanes by killing them, by extracting their energy and awakening them. That's why it's so important to not only track where the loop current eddies are going to be, but also where this loop current frontal eddies will be in regards to the track of a hurricane. Okay, so these frontal eddies, they can also affect the balance of force in the loop current system. So they can be so strong that the centrifugal force associated to this eddy can be important and not neglected anymore. So in most cases in oceanography, when we have large currents that flow slowly, we assume that there's only 2 forces playing a role: Coriolis force, which is the force associated with the rotation of the Earth, and the pressure gradient force. And this is valid for most times, but for this specific case of the loop current system, when we have strong frontal eddies, this assumption is not valid anymore, and we have to take into account the centrifugal force. So this is important when we're deriving, for example, velocity field from altimetry. We have to take into account the centrifugal force as well. And finally, these frontal eddies, they can play a role in transporting water around the eastern Gulf of Mexico. So when this frontal eddies get strong, for example, here we have 2 cases, a case of a weak frontal eddy and a case of a strong frontal eddy. we can see that there's a corresponding increase in the velocity field. So if you look on the right, two right plots, this figure is corresponding to a cross section in the center of the loop current, and in sampling the loop current from and the loop current frontal eddy. And so the color is temperature, and the white lines are velocity from mooring. So it's total velocity that measure the flow from the surface down to 1100 meters. And so comparing these two figures here, in the case of a weak loop current frontal eddy and a strong loop current frontal eddy, you can see that the flow at the interface, so over here the front, becomes much stronger. And then you have a tilting of the isopycnals as well, as if the frontal eddy is squeezing the loop current and then getting the front even more strong. And why is this important? This is because when you have a strong flow, then you can attract water from the surrounding. So in this figure here, we can see a map of sister phase salinity. So very fresh waters come the Mississippi rivers and being trained around the loop current and in the interface between the loop current and a loop current frontal eddy. So these two features, loop current and the frontal eddies, they rotate in opposite direction. One rotates clockwise and another one rotates counterclockwise. And we know that this motion can actually attract fluid, can attract chlorophyll, for example, which are microalgae that are present in the coast mainly, so they can be attracted in this front, fresh water, and other passive traces. But what intrigued me is that it's known that these two features attract water to their interface, but during the 2010 Deepwater Horizon oil spill, water not only got entrained at the boundary, at the front, but also inside a loop current frontal eddy. And this oil remained there trapped for weeks. So during the Deepwater Horizon, many oceanographers started running models to trying to predict where the oil would go. And most models were actually showing that this oil would flow the loop current front and would reach the Florida Keys, which was a big worry at the time. People were getting ready to clean the beaches already on the Florida coast. But it turns out that when this frontal eddy intensified on the north side of the loop current, it attracted all the oil, and the oil never reached the Florida Keys. And so that made me wonder, what are these properties of the frontal eddies? So that means that they are able to trap and conserve and transport oil in their interior without exchange with the exterior for a certain amount of time. And this is the definition of Lagrangian coherence, when a vortex is able to trap water and there's no flow across the boundary. And so the question that I ask myself are the loop current frontal eddies Lagrangian coherent vortices, which seems like they are, right? So can they transport fluid particles from one place to another without exchange with the exterior? And then for how long can the frontal eddies remain Lagrangian coherent at and below the surface? And then ask myself, what's the source of water for the formation of the frontal eddies? And finally, the implication of this coherence to the surrounding flow. Can it drive cross-shelf exchanges? And so these results I put together in a manuscript that I submitted to Progress in Oceanography and is currently under revision. So to study Lagrangian coherence, there's one specific method that it actually suits very well the problem. And the reason why we use this method is because Eulerian methods, such as relative vorticity, SSH contours, Okubo-Weiss parameters, they actually fail to identify the boundary of coherent eddies. And a simple test can be done by placing particles inside those contours and advecting forward. And you can see that after a few time steps, these particles start leaking outside the eddy starts filamenting and losing its content. So to identify actually the boundary of a coherent eddy, we have to use something a little bit more sophisticated. And so Haller, Baron, and Vera 2013 developed this method to identify coherent boundaries of Lagrangian vortices in 2D flows. And it's based on a simple concept that there's in this boundary, there's no transport across the boundary. So there's no water that ends in the boundary, and there is no water that leaks out of the eddy to the outside. So this is actually by construction. This is how the method was developed around. And so we can find these boundaries that defy the typical exponential background exponential stretching of the ocean. And this method is also observed independent, which means that if we change our frame of reference from, for example, Earth's frame of reference to a frame of reference co-rotating with the eddy, we will obtain the same result, which is not the case with other methods. And so, for example, here, this, so Haller, Barone, and Vera 2013, in their paper, they applied their method to the Gauss eddies, and they found that some of the eddies can remain Lagrangian coherent for up to 200 days before they start filamenting. And they also show some other examples of velar encounters that they advected forward, and you can see that very fast they start filamenting and losing their coherence. And so Haller and Barone and Vera developed the method, but Daniel Karash actually wrote a code on Julia that detect in an automated way the coherent Lagrangian vortices. And so I'm just going over quickly the method so you can have an idea how it works. First, it's a Lagrangian method, so it's based on calculating trajectories. So the code first calculate trajectories, then it compute the flow maps, the flow map from the trajectory, which describe the evolution of the flow. And then from the flow map, it calculates the Cauchy-Green strand tensor, which the Cauchy-Green shows how the flow is being deformed from time 0, the initial time, to a final time t. And from the Cauchy-Green strand tensor, we can obtain 2 eigenvalues and 2 eigenvectors, since my trajectories are in 2D, right, in space. And so once you have this eigenvector and eigenvalues, and you can actually compute strain lines. So these strain lines show where it's stretching, where the flow is very strong, converges, and remain together. And the strain lines, they are tangent to the eta fields that are computed with this eigenvector and eigenvalue. So it's a lot of a bit heavy theory, but the main point is that when you plot the maximum eigenvalue, so this is a color map of maximum eigenvalue, superposed with the vectors of the eta fields. You can see over here. So you can see that the stretching of, in this field, I applied the method to the loop current. So this is the loop current boundary. And this is what I saw from altimetry that corresponded a bit to a loop current frontal eddy, right? It was a cold core. And so I applied this method to see where the method would find a coherent boundary. And when I did that, I found a coherent boundary that was actually over this domain over here. And I applied this method for 17 days for this specific case, which means that in this contour, all the particles that were inside the contour remain together for the following 17 days. Okay, so I applied the method to 2 data sets. The first one is a 1 kilometer resolution free run HICOM that was ran from 1994 to 2003. The time that I did the research. Now they have data up to 2010. And so HICOM has pressure levels at the surface and isopic coordinates in the open ocean. And then I also applied the method to sea surface height and geostrophic velocities from Aviso for the 2010 Deepwater Horizon. So I'm going to first start showing the results from the model. So when I found that for 2 cases, one in 1999 and the one for 2001, this is the model and it's a free run, so does not correspond to any of the real loop current state. But I found that, well, it reproduced the loop current dynamics, but not real cases. And I found that for the case of 1999, a loop current frontal eddy remained Lagrangian coherent for 18 days. And for the 2001, it remained Lagrangian coherent for 10 days. And so that was at the surface. These 2 plots figures here are the same one as the one in the previous slide. But if you look at deeper layers, for example, layer 16, that it's located around 100 meters, for both cases, so I got 23 days for the 1999 case and 15 days for the 2001 case. And then if you go even deeper, so layer 23, 24 in the model, which corresponds to around 200 and 250 meters, the loop current frontal eddy remain even more Lagrangian coherent for longer. So 29 days for the 1999 case and 19 days for the 2001 case. So overall, we can see the frontal eddy can remain Lagrangian coherent for longer at deeper layers. And you can see that the contours also are slightly bigger. So not only they can carry particles for longer below the surface, but also larger amount of water and particles. And below those layers, the eddies actually start losing Lagrangian coherence. And so they carry water for less time. And so to validate a little bit and what I found, I placed 6,000 particles inside the first loop that I found, and I advected forward using a fourth order Runge-Kutta method to the velocity field. This is still the model. And so you can see that for this case that I found that the eddy was coherent for 18 days at the surface. You can see that for 18 days, all these particles remain together until the shedding of the loop current. But the interesting part is actually to do a backward advection, because then we can find out where the water that forms the frontal eddies come from. And before I play the video to you, just I wanted to name a bit the shelves. So in the blue hatched area shows the West Florida shelf, and the yellow one is the Mafla shelf, which is the Mississippi, Alabama, Florida shelf. So you can see that all these particles, I'm going to stop the video here at the beginning. There's a lot of particles that come from the Mafla shelf. And well, so to some extent, particles that come from the Mafla shelf, and some others that come from the West of Florida shelf. And the rest of the particles come from the outer band of the loop current front. These particles converge. They start getting structured. There is some vortex merging. You can see like two vortices getting together in a line. And then it gets organized, and there's a formation of this coherent frontal eddy that remains and conserves its water for 18 days until the shedding of the loop current. I did the same thing below the surface, so at 200 meters. And for this case, you can see already that there's much less spreading, and that most water actually comes from the outer band of the loop current front. So it's a bunch of many small vortices that are carried on the loop current front that start merging, getting together, and becoming larger and stronger. And so the eddy becomes coherent and then remain Lagrangian coherent for 29 days until the shedding of the loop current. I was also curious to find out what was the fate of the water inside the frontal eddies once they lose their coherence. So for the case at the surface, I placed particles, but instead of advecting backward, I advected forward for 60 days. And so this is the time that the eddy is still coherent. And then when the shedding happens, the eddy loses coherence. And these particles actually get very fast entrained around the loop current eddy. And I would like you to notice that there's no particles that cross the loop current eddy and enters in its interior. And this is because the loop current eddy is also a Lagrangian coherent eddy that was studied by Biron and Vera et al. 2018. And then eventually, in this case, this loop current eddy reattached with the loop current. And so creating this strong flow that advected all the particles eventually like outside the domain. So these results were shown that I showed until now are with the models. If we look at altimetry, so if you remember this animation that I showed at the beginning of the talk, where you have the loop current, a frontal eddy gets strong and drive the shedding, and then two other eddies that intensify, one on the north side and one on the south side of the loop current eddy. These are the same eddies here that I shown these figures. And so I did the same analysis, and I found that for these three eddies, the Lagrangian, these frontal eddies remain Lagrangian coherent for 20 days. And so I also place particles in the loop current frontal eddy that lead to the shedding of the loop current. And when I play the animation, you can see there's lots of particles that come from the Maffler, well, yes, from the Maffler shelf. These particles converge, and the other part comes from the outer band of the loop current again. You have these two smaller eddies that converge around each other. The particles get organized, and then it leads to the shedding of the loop current. This black diamond over here is actually the location of the deep water horizon. And so just go back to a second here. So this is the eddy, the frontal eddy that leads to the shedding of the loop current. But this frontal eddy here on the north side of the loop current, it's actually the frontal eddy that attracted oil into its interior and conserved it for the following weeks. And so I did the particle analysis with this eddy as well. And if I play the animation, you can see once again, you have particles coming from the Maffler shelf, some other particles coming from a little bit all over the eastern Gulf of Mexico. And I'm gonna stop at April 20. Oops, I didn't do that. If I go to April 20th, this is the date actually that the oil rig broke and started leaking oil to its surface. And so that's when the oil started flowing, some part of it towards the beach, but the other part got advected exactly as a filament, as you can see here, and it got entrained in this growing frontal eddy. And so our results correspond well with previous results and also altimetry maps of the location of the oil, the spread of the oil during the Deepwater Horizon. And so we answered the first set of questions about the Lagrangian coherence. They are Lagrangian, frontal eddies are Lagrangian coherent structures, and they can remain Lagrangian coherent the surface and below the surface, but mostly we saw that the Lagrangian coherence increase as we go deeper up to around 200, 250 meters. And then the two last questions, the source of water from the formation, and then the cross-shaft exchange, we addressed it until some extent, right? So I did a further analysis to look at the water masses of the loop current frontal eddies to make sure actually that what we're seeing with the particles correspond to the what's actually happening. So we saw with the particles that most of the water come from actually the Gulf waters, right? There's no particles coming exactly from the interior of the loop current, but the particles being transported by the loop current front, it's not very clear if they're transporting loop current waters or if they're only transporting Gulf waters. And then for the cross-shaft exchange, I also dig in a little bit in the observations to get some light on this question. And so first looking at the water masses in the loop current frontal eddies in the other environments, I use aircraft expandable profilers. So these are probes, so CTD probes that were released from the NOAA aircraft, the Hurricane Hunter, and they were released actually during the 2010 Deepwater Horizon to help assess the position of the loop current relative to the site of the oil rig. And I separated the profiles that were in the sample each environment. So we have the loop current environment, Gulf water, the loop current front, and the loop current frontal eddies. So you can see that the loop current, actually, it's the water, the density and the water properties are very homogeneous along the water column, and there is not much spreading. So you have here, this dot here represents the the reference temperature and salinity of the Gulf common water, which is the typical water of the Gulf of Mexico. And then you have here the North Atlantic subtropical underwater core, which is typical of the loop current water. So can show that our temperature and salinity profiles, they sampling the loop current, they are in agreement with previous study that found that the core of the loop current of the water masses is located in this and with these properties of density and temperature and salinity. And so the Gulf water environment actually shows the temperature and salinity that's aligned with the water common of the Gulf of Mexico, which is also in agreement with literature. Then when you look at the loop current front, we can see that there is a mix of properties, temperature, and especially salinity between the loop current and the Gulf water environment. So there is this range of profiles and density structure that corresponds to both features. And then finally, the loop current frontal eddies. You can see that the temperature and then salinity, so this TS diagram, it's much more similar to the properties of the Gulf water. It's closer to the core of the Gulf common water compared to the core of the loop current. So this result actually confirms what we saw with the particles, that the water forming the frontal eddy is mostly composed of Gulf water, and there is no much water from the loop current actually being drained in the loop current frontal eddies. I did the same analysis using the model, and then the results are similar. So I took a sample inside the loop current, another one outside. So this is representative of the Gulf water, another one on the front, and another one inside my Lagrangian coherent boundary of the loop current frontal eddies. And I found that in the loop current, again, you have a very homogeneous profile. You can see that all the profiles are a bit displaced in the salinity range. And this is because HICOM and other models, they sometimes have some imprecision with salinity due to the lack of in situ measurements for initial and boundary conditions. But since we're interested in the mechanism, and this is a free run, so it was not readjusted to real temperature and salinity, this is very satisfactory in terms of result. And so the Gulf water has a range of salinity that's much larger, but still you can see that all its properties, it has salinity fresher than the one that we find in the loop current. And then the loop current front environment, again, has a range between loop current and Gulf waters. And finally, loop current frontal eddies have water mass that are very similar to the Gulf water and not so similar with the loop current. So this confirms that the loop current frontal eddies are formed from water coming from the Gulf water, not from the loop current. And then finally, for the cross-shelf exchange, I look at first at chlorophyll. So chlorophyll is a good proxy to understand where water is being carried, because it has this very strong signature from satellite. So for this case of loop current with two very strong loop current frontal eddies, you can see that the corresponding chlorophyll map has these filaments of water, right? And then rich in chlorophyll being attracted to their front and to some extent looping around. And you can see the second filament over here going in the direction of this second loop current frontal eddies. And so this is some indication that we have this corresponding this communication between offshore and then inshore. And then I would like to also mention that in our videos, there were no particles coming from the inside of the West Florida shelf. And there is a reason for that. There is what's called a transport barrier in this region that was named Forbidden Zone by Olasquaga et al. 2006, that showed that there is actually a strong flow that flows in along the bathymetry in the West Florida shelf, and then finally reaches offshore waters. And so this front actually isolates the West Florida shelf and doesn't land anything that is inside the West Florida shelf to go to offshore regions. So it's rare to find particles and or even drifters that are being transported offshore. And so our results are in agreement with this forbidden zone in terms of not finding particles crossing this transport barrier. And I also look a little bit at drifters. So this is a data set from Lily and Paris and Brunius 2021. So they took all the drifters available in the Gulf of Mexico, a very nice data set. And there's around 2,000 drifter trajectories in the eastern Gulf of Mexico. And they also have another average project. And in their average project, I'll like to go back here, you can also clearly see this jet of water being transported along the West Florida shelf as well. And so using this drifter trajectory and this drifter data set, I found a couple of trajectories, and I'm just showing 6 over here. Trajectories started in the West Florida shelf or in the Mafla shelf, and that end up crossing the isobath and being trained either around a loop current frontal eddy or in its interior. And so you have here, in this case, the first map, this particle that was in the West Florida shelf, and then crossed the isobath and going trained a loop current frontal eddy. And you can see that this drifter is not really inside. So when I talk about this jet that isolates the West Florida shelf, it's important to say that this jet actually moves inward and outward in function if it's summer or if it's winter. And so I'm guessing this jet was probably slightly more inward in this case, which allowed for the crossing of this particle and the isobath. We have 2 other trajectories here. Is the same thing. You have this drifter that started inside the West Florida shelf and was entrained around a loop current frontal eddy. And then some others that started in the Mafla shelf, so the north of eastern Gulf of Mexico, crossing the isobath as well. This one over here actually got entrained to 2 loop current frontal eddies and eventually follow its course. And so these drifters and the chlorophyll maps provide us some indication to some extent that the frontal eddies could be playing a role in leading cross-shelf exchange. And this, if it's not completely proven, but if it was true, then that means that this is an important process to actually bring waters full of chlorophyll, full of nutrients from the coast to oligotroph water, so water poor in nutrients in offshore regions, and which can have an impact to fisheries and other water mass properties. For example, if it entrains a lot of fresh water to offshore regions. And so, as concluding remarks, for the part of the Lagrangian coherence, we found that the frontal eddies can remain Lagrangian coherent for weeks, so up to 18 days at the surface for the model and 25 days for altimetry. I showed 3 cases here in altimetry that found Lagrangian coherence of 20 days, but I also look at other cases that remain Lagrangian coherent for up to 25 days. And then we also found that the frontal eddies can remain Lagrangian coherent for longer at deeper layers, up to 29 days at 200 meters. And then frontal eddies start losing coherence below 200 meters. So for the source of water, we found that the frontal eddies are composed of Gulf water. And so they are formed by, or they are formed by the convergence of water from the loop current front outer band, the region north of the loop current, and the Western Florida shelf and the Mafla shelves. And I let it clear here, it's the Western West Florida shelf. Again, highlight that there is not much water that crosses from the Eastern West Florida shelf to the offshore regions. And finally, loop current frontal eddy formation could drive cross-shelf exchanges of particles, water properties, and nutrients. This is something that we have to work a bit more to be sure that this is really true. But so far, our results from altimetry, from the model, and also looking at drifter trajectories in chlorophyll converge towards this mechanism or this process happening. And our overall conclusion is that the loop current frontal eddy formation and propagation actively modify the surrounding circulation and are essential for predicting the evolution of the flow and the transport of oil and other passive tracers, chlorophyll, freshwater in the Eastern Gulf of Mexico. And with that, I'll take any questions.
Wonderful. Thanks so much, Luna. Let's have some questions for Luna. And as we're doing that, I would really appreciate to find out kind of who's in the audience. So if you could just write in the chat your name, where you're from, and what your field is, that would really help me get a feeling for the audience. So I'll start there, so you know who I am. So please do that as we're listening. So go ahead, James. You have a question?
Yes. I was interested in the fact that there was less Lagrangian, shorter Lagrangian time near the surface. And I was curious why that was, and is it just that the Ekman flow can blow things across geostrophic streamlines, or is it something else?
Exactly, that's why we're thinking it's mostly because of the winds. And so that can lead to higher energy and higher frequency motions that end up spreading more the particles around. So that's why we have less, so the frontal eddies remain coherent for less time, but also there is smaller amount. You can see that the loops are also smaller. So it's actually, when you compare satellite and our loop contours, you can see that the satellite has this sister phase height signature much larger. And so there is much more fluid in motion, but wide remains Lagrangian coherence. What's conserved is the interior. Whereas when you go at deeper layers, and this loop has a tendency to go larger due to the slower motions and low frequency motions.
Thank you.
Some more questions?
Oh, there are people from all over.
Yeah. Well, I'll ask you one, Luna, while we're waiting. Can you tell us more about the relationship between the frontal eddy formation and the detaching of the meanders? I know this is something I think you've worked on in other areas, but I recall having seen some hypotheses that maybe it's that the meanders are forming, and as it's pinching off, it sucks in these eddies rather than having the eddies being a causal factor. So can you kind of walk us through the dynamics of how the formation is linked with the loop current eddy pinch offs?
Yes. So the thing is, there's many mechanisms that are happening at the same time. Not only they're formed through baroclinic instability, but also there's vortex merging that can lead to intensification of these frontal eddies. There's also alignment, so vertical alignment of the eddies. They stretch when they pass through steep bathymetry, particularly in the Mississippi Fan on the northern eastern of Mexico. And so all these mechanisms lead to an intensification of the frontal eddies. And when they intensify, we can also see an increasing of the meanders. So your question, what leads what? I think there's one paper in particular, Zonahue et al. 2016, that look at how the signature that we see of the frontal eddy at the surface, it's also linked to a deeper signature of a frontal eddy. And so it's not really certain if this is part of the loop current frontal eddies or not, these deep eddies, but they're also cyclonic and they tend to align to some extent. And so when a shedding happens, we see this propagation of the deep eddies westward first, and then the growing of the meander and the loop current frontal eddy propagating westward with the deep eddy. And so then that raises the question of this deep water, this deep cyclone is growing at the same time that the meander is growing and that the loop current frontal eddy is growing. So what is leading what? So far, mostly we attribute the shedding to the loop current frontal eddy, pitching off the loop current. But it feels that they do entrain each other and they do feed up each other. So it's a joint process where you have this frontal eddy intensifying and the meander increases, then which leads to more entrainment of water. You have more shear, you have more relative vorticity going both sides, positive and negative relative vorticity, which leads to a tilting of the isopycnal. And so, which feeds up a more intensification of the flow. So everything, it enters into a loop that it both leads to a growing of the meander at the same time that also grows the loop current frontal eddy until the pinch off. What we have found though, is that sometimes this deep eddy propagates westward in the neck of the loop current, but the surface signature of the frontal eddy does not go with. And if that happens, the frontal eddy of the surface doesn't follow the deep eddy, then there's no shedding. That's what that makes me think that the frontal eddy plays a first role in the shedding and primary to the meander. But I think we would need to do some more analysis of, for example, potential vorticity fluxes to really understand exactly what is driving what and when.
Thank you for that answer, Luna. Let's take the question from Ben that's written here in the chat. He says, well, when you're applying the Lagrangian structure method, how dense do you need the particle trajectories to be?
How dense?
Yeah, how dense?
What kind of like spatial coverage do you need? Like how dense these particles have to be?
Yes. So for this method, so okay. I think you have two things. You need to release a lot of particles, but you also have to make sure that your data set is high resolution enough, because if you have a low resolution field and you deploy a bunch of particles, then you're not going to really sample the structures. So I would say for the spatial resolution of the data set, maximum of a quarter degree, which is the resolution of altimetry. If you go lower resolution than that, then it will be hard to detect the features. And for the resolution of particle release, I used a quarter kilometer. So 250 meters. I tried with less, and that would give me pretty much the same result, but I went higher resolution to make sure I was getting the most optimal contour.
Perfect, thank you.
Mm-hmm. And so the 220, so the quarter kilometer was for the model. If you go with altimetry, then you'd use less particles because it has to be proportional with the velocity field that you're using, the resolution. But I feel like you still want to go high resolution enough. Yeah, enough particles.
Yeah, thank you very much for the talk. Very interesting. I was wondering, my question is related to the previous one somehow. I was wondering if the Avisa altimetry data you were using is coarser than the model data, right?
Yes.
Is that correct? Yeah. So what do you think? It might explain why your coherent structure in altimetry lives longer. Probably. I'm just curious.
Definitely. Also because we are not really solving the high frequency motion in altimetry, since the fields are so smooth out. So you end up losing so much of structure that this is definitely affecting our results. So it's really a combination of which one is true. We have altimetry that it's taking as the truth, but it's so smooth out and we're losing so much information, then we go back to the model and being like, it seems like the model is representing more the reality, even though it's a free run. So it's hard to get, you know, the real answer. What is the truth? And I thought about going to the high resolution model with data simulation. When I started this study, we didn't have this option, but now the 1 kilometer resolution Gulf of Mexico has a newer version with data assimilated to it. And so that'll be interesting to repeat the same analysis and see if we obtain a Lagrangian coherence time that's a bit similar. That's a good point. Yeah.
Yeah. Thanks a lot.
Thank you.
Great. Well, thanks a lot, Luna, and thanks everyone for coming, for the great questions. We'll go ahead and we'll end the official talk now. So thanks for coming. And then anyone who's interested to stick around, what we normally do afterwards, you know, we can't take the speaker to lunch,